Hello everyone, in this video we are going to be determining precision and accuracy. Alright, so before we hop to their formal definitions here, this is a very typical representation of accuracy and precision as far as measurements and data are concerned that you might see when you get to any statistics section of a book. Alright, so if I were to look at the top left, this has low accuracy and low precision. So all of my points here are spread out and they are not where I want them to be in the bullseye here. Alright, so if I keep the low accuracy but switch to high precision, all of my darts here have made it into the same area. So my data points there are closer together, however they still aren't on my bullseye. So that is low accuracy, high precision. If I go to high accuracy but low precision, they are all surrounding my bullseye here, but they are not very close together. And then finally, high accuracy, high precision, all of my darts are in that bullseye and they are all together. So, all measurements are approximations. The length of each segment below, so the red and the blue one here, to the nearest inch is 2 inches. Alright, notice the blue is a little bit longer here, and the red is a little bit shorter. So the measurement is to the nearest inch. So the unit of measure for this example is 1 inch. If, however, you were told an object is 2 inches long, you know its exact length is between 1.5 and 2.5 inches, or within ½ inch of 2 inches. The greatest possible error of a measurement is equal to 1/2 of the unit measure. Alright, so whatever the unit measure is, I just chop that in half, and that becomes my greatest possible error. When the unit measure is smaller, the greatest possible error is smaller, and the measurement is more precise. So if I go back to my darts here, when I'm looking at the high precision, we are looking for those data points to be closer together. Alright, so using 1/8 inch as the unit of measure for the segments above gives the length of 1 6/8 inches for the red and 2 3/8 inches for the blue. A greatest possible error of 1/16 of an inch, because if we were talking about 1/8, divide that by 2 and you get 1/16. Okay, so let's look at example 1. Amusement park. The final drop of a log flume ride is listed in the park guide as 52.3 feet. Find the unit of measure and the greatest possible error. So, 52.3 is rounded to the nearest tenth of a foot. So, the unit measure here is 1/10 of a foot, which means the greatest possible error is half of that unit measure, so 1/2 times 1/10 equals 1/20th, or 5/100ths, or 0.05. So the greatest possible error is 0.05 foot. Relative error. The diameter of a bicycle tire is 26 inches. Alright, the diameter of a keyring is 1 inch. So in each case, the greatest possible error is 1/2 of an inch, because all of these are just in inches. Alright, so a half of an inch has a greater effect on the diameter of a smaller object. So if we're thinking about two really extreme situations here, is that, a difference of buildings, if I'm creating all of these houses that are, carbon copies, they're exactly alike, if one house is a half of an inch off, as far as how big the floor plan is, that's not going to make as much of a difference as it would if I were talking about, creating a retainer for somebody's braces or something like that. A half of an inch in your mouth is, that could be the difference between you, having a huge gap or not in your smile. So it has a huge difference when we were talking about smaller objects. Alright, so the relative error of a measurement is given by the ratio the greatest possible error divided by the measured length. So as you can see below in this example, I have the tire versus the key ring. So the half inch is still on the numerator for both of them, but then the actual measurement of my tire and the key ring are in the denominator. So my relative error is approximately 0.01923, or about 1.9% for the bicycle. And for the key ring, it is about 0.5 or 50%. So the measurement with the smaller relative error is said to be more accurate. So that means the bicycle, in this case, the bicycle tire, is more accurate. And if we look at our note on the left here, precision depends only on the unit of measure, that's precision, whereas accuracy depends on both the unit of measure and on the size of the object being measured. Right, so accuracy depends on a little bit more. Alright, here in example 2, playing areas. An air hockey table is 3.7 feet wide, and an ice rink is 85 feet wide. Find the relative error of each measurement. Which measurement is more accurate? So, the unit of measure for the air hockey table, since it has a 0.7, it is measured to the 1/10 of a foot, whereas an ice rink is measured to the nearest foot. So the unit of measure is a little bit different for both of them. And then I take 1/2 of the unit measure for the air hockey table and 1/2 of the unit measure for the ice rink in order to find my greatest possible error. So then, to find the relative error and determine the accuracy, I take my greatest possible error over my measurement, greatest possible error over my measurement, and I get a percentage. So, for my air hockey table, it comes out to about 1.4%, which is pretty low. But the ice rink is even lower at 0.6%. So the ice rink has a smaller relative error, which means it is more accurate. Alright, so here are your practice problems for this extension video. Please feel free to send me an email with any questions that you have, and I look forward to hearing from you. Good luck!